Hi guys, welcome to the channel. So today we are going to talk about the formation of absorption bands in UV visible spectroscopy. So whenever we see any spectra in UV visible spectroscopy, then we observe that we do not get sharp peaks. Instead we get those broad bands instead of the sharp peaks. So basically we want that our expectation is actually that we would get sharp peaks, and each sharp peak will be corresponding to the particular excitation from the ground state to the excited state, but that is not always the case. Actually, that is never the case. We never get the sharp peaks, instead we get the broad bands. So why it is so, we are going to discuss that in an elaborate way. So now we are going to talk about the formation of absorption bands. Now, this thing we have discussed earlier, that whenever we get some sort of spectra in UV spectroscopy, then that graph between absorbance and wavelength that we never get a sharp peak. Instead, we get some broad bands. We do not get the sharp peaks. So, why is it so? Now we have discussed this thing in molecular formulas and structures also. There is one topic which we are about to use here, so I would highly recommend you guys to just watch that video first and then come to this video. I'll provide you the link in the description down below. So in that video we have discussed a spectra, which is like, here we have the radio waves followed by microwaves, then we have IR, and then UV, X-ray, gamma, and then cosmic. Now this is in order of decreasing energy. Decreasing energy means cosmic rays will be having the highest energy, followed by gamma ray, X-ray, UV, IR, micro, and radio wave will be having the least energy required for their transition or whatever they want to show. Right? This is in terms of energy. And if we want to talk in terms of wavelength, then in terms of wavelength, it is just the opposite. Cosmic rays will be having the least wavelength, and radio waves will be having the highest wavelength required. Right? Highest wavelength required for their transition. Now why this is so? Because we know formula E is equals to hc by lambda. From here we know E is inversely proportional to lambda. Right? If energy is highest, then wavelength will be least. So this we have discussed already in molecular formulas and structures. Now, if we are operating in UV region, right? We are talking about the UV spectroscopy. So now if we are operating in UV region, then that means it will be having some sort of energy which is higher than that of IR, micro, and radio waves. Right? This is very important concept. We need to understand this very thoroughly. So if we are operating in UV region, then that means that amount of energy which is required for transitions in UV region, that energy will be already be sufficient for IR, micro, and radio waves. Right? Because this is the higher energy as compared to IR, micro, and radio waves. Right? So if we are operating in UV region, then if we talk about the IR region, which requires the lower amount of energy as compared to UV. So in IR region, vibrations are observed, right? In microwave region, rotations are observed, right? We will talk about these two only right now. In IR, we are having vibrations, and in micro, we are having the rotations. So we'll better write that. Here we will have vibrations, and here we will have rotations. So if a molecule is showing electronic transitions in UV region, then those transitions will be having vibrations and rotations associated with it already, because that amount of energy will already be sufficient for vibrations and rotations as well, which is causing the electronic excitations in the molecule. Why is it so? That we know, because the amount of energy which is required for operation in UV, that is already sufficient for these regions, right? These regions require much less energy as compared to the UV region. So molecule, if it is showing the electronic transitions, then it will also show vibrations and rotations, right? So pictorially, if you want to represent it and if you want to understand it better, then how will I do it? Now suppose we have two energy levels, right? We have two energy levels. These two energy levels, E1, E2. These are the two energy levels for UV transitions, right? So in between these two energy levels, there will be vibrational as well as rotational energy levels. So if I talk about these two levels, then those will be, this is E2, this is E1. So there will be like vibrational as well as rotational. Suppose these are the vibrational energy levels in E1, these are in E2. These are vibrational energy levels, right? Now in between these vibrational energy levels, we will be having the rotational energy levels. In between these, we are going to have some rotational energy levels. Right, these are the two energy levels in between which electronic transitions are about to happen, and in between these two energy levels we are having the vibrational energy levels, and in between each of these vibrational energy levels we are also having the rotational energy levels. So what happens in this case, if we are talking about a transition which is taking place from this to this, then the transitions can take place, there will not be one single transition. Transition can be from one vibrational energy level to the other, right? It could be from one vibrational energy level to the other, or it could be from one rotational energy level to the other, right? There are so many possibilities of transitions, so there will be no single transition, there will be multiple transitions, and due to these multiple transitions will form sort of a band. Instead of a single peak, it will form a sort of a band, and that's why we do not get a sharp peak, we get a broad band, because we get multiple transitions from each vibrational or rotational energy levels, and due to these multiple transitions this sort of a band forms instead of a single peak, right? Also, there is one more important point. So right now I'm going to talk about UV plus visible region, right? UV plus visible region. So roughly if we talk about these two regions, then from 200 to 400 we are having the UV region, and from 400 to 800 roughly we are having the visible region, right? If we are operating in UV region, then we use the cuvettes. Which we use cuvettes are like this, they look like this, which we insert inside the UV spectrophotometer, and two of their sides are completely transparent, two are slightly translucent. So the transparent sides are like from here to here, this particular side and this particular side, from where the light will pass, and the front and the back, that will be slightly translucent. And this is sort of a cuvette which we insert inside the spectrophotometer, and inside the cuvette we have the solution which we want to like analyze. So this cuvette, if we want to operate in UV region, this cuvette is made up of quartz. And if we are operating in visible region, then this cuvette could be of glass. But it is highly recommendable if you are using it in UV region, you are going to use cuvette which is made up of quartz. Now why this is so? Very simple reason is there, because glass absorbs more radiation as compared to quartz, right? So whatever radiation we are about to provide to the solution, this particular cuvette is about to absorb that radiation. So in order to avoid that situation, we use quartz so that it would not absorb the radiation which we provide for the solution. So we use quartz in UV region. In visible region we can use glass as well, there is no issue with that. But in case of UV region we have to strictly use quartz, because it does not, or it absorbs light but very less as compared to glass. So we use quartz cuvette. So this is all about the formation of absorption bands. That is why we get broad bands instead of sharp peaks, and why we use quartz when we are operating in UV region. So that's it for this particular topic. We will move on to the next topic of, maybe it is going to be concept of chromophores and auxochromes.